So have anyone remembered to think about St. Petersburg paradox? I should have mentioned to think about it again, but you have you remembered it, guys, or forgotten it entirely? So this was the question. Suppose that you have one fair coin and it will be flipped randomly until the first heads arrives. Once you get your first heads, that if it's on the nth trial, you will get 2 to the power of n dollars as reward, right? So if it's on the first trial, you get only $2. If it's on the second trial, you get $4 for the first time, etc. And the question was, would you wager $1 million to play this game? And of course, with this condition, right? You don't have $1 million, you can take a loan. And the loan will be, in other words, you can take as many loans as you need for every game until you decide to pay and leave the table. Okay? Would you have played this game?
I have a quick question about it. Let's say on the first toss you get a heads. Are you allowed to keep playing or you're done?
No. So you get $2. You spent $1 million and you got $2 as your payment. Yes.
Okay.
But the $1 million is for the entire game, and you don't have to pay until you decide to leave the casino. You understand?
So if you got heads,
they ask you, do you want to play another game? If so, they will take away another $1 million. In other words, now you owe $2 million to the casino, and now you play the next game, and you continue doing that until you decide to quit.
I don't think it would be. I think if it was like a dice with a specific number that it had to be, then yeah. But if it's just a coin, there's only 2 options. So it seems unlikely that, because to get to like, because if you have to take out a loan $1 million each time to play, then you need around like 19, 20 like tails in a row to get to that 1 million to break even. So I don't like getting 20 tails in a row is very unlikely.
I see. That's a good observation, guys. Anybody else, guys? You're here. Did you have anything to say about it, guys? Have you thought about this problem? So here I offer you this game, and would you play it? It is. If you say it's called St. Petersburg paradox, there must be something paradoxical about it. Yes. So Kazi wouldn't play it. I mean, you of course are. You can be a suspicious bunch. I'm not lying, right? Let's say this game is truly arranged this way. So that would be so. Yes. Everything you hear it's so, and you can keep playing until you decide to leave. You say you only pay the casino once you decide to leave the table. What about the rest of you guys? What about you, Alejandro? You're often very quiet, but you have interesting things to say. Do I have an Alejandro is here? Yes, you are here. Guys, so here is, if you're just joining, this is what I am talking about. You see, I'm not sure, I should have mentioned in my email, I forgot to remind you to think about St. Petersburg's paradox. And the idea is this: you take a coin, and it's a fair coin, and you flip it until the first time it comes heads. And if it's on the nth trial, nth toss, then you get 2 to the nth dollars. So in other words, if you threw the coin 3 times in a row, and it was tail and tail and tail, and then next time is heads, the 4th toss is heads, then you get $16, 2 to the 4, yes? So for each game, you have to wager $1 million. And of course, you don't have that money, but the casino is willing to give you that loan. Okay, and not only for one game, you can take another loan for as long as you like until you decide to leave the table. In other words, if I want to play 20 games, I can borrow $20 million. If I want to play 1 million games, I can borrow 1 million multiplied by $1 million.
I have another question.
Yes.
So if you get a heads and you start a new game, does n go back to 1 or does it keep getting larger?
No. So the game always restarts, right? So each game you play, it's from start, right? You don't really. It's just until you get your first heads. Okay, so Murshika is saying it feels like the money would keep adding up. So Alejandro, what do you think? I'm sorry, I pick on you. What do you think, Chabeli, and the guys that are joining in, Valeria, maybe Paula, I would be very happy to hear from. Yes, so you all wouldn't play it, but you see, it's a very interesting thing. There is this intuition that people have, and there is knowledge, and there is something between, and maybe you can still call it intuition, but it's something in between. You agree? Right? So you cannot really voice it, but something bothers you about it. So that means maybe that's what people call intuition, right? I don't know if it's just maybe. Yeah, they don't have always a good word for it, I think. Yeah, but so okay, I will explain how I thought of this problem. Good. So first of all, do you remember what is expected value, guys? Do you all remember what expected value is doing? Do you have a good mental picture of what expected value is? If I were to play this game, right, and look at the scores of each game, right? At the scores of each game, let's say I played 50 games. If I play 50 games, I already have 50 minus 50 times million. Do you agree? Because I always lose for each game $1 million. And then I have some winnings. So sometimes it's 2, and sometimes it's 4, and sometimes it's 16, right? And all sorts of numbers, right? So in the table, I add up all my winnings and then average the winnings and subtract $1 million. Do you agree? That's what I do when I look at the table. Imagine that you play the game 1 million times. Do you agree? 1 million times. So you have a table that has a column that's 1 million entries long, and in those entries you see, the particular score you won minus $1 million. If you add up all the scores, you will get 1 million minus $1 million multiplied by $1 million, plus the sum of the positive winnings. And then if I divide it all by $1 million, it will be the average of all your positive winnings minus $1 million. Do you agree? Guys, so I'm talking about it. I hope you understand what I mean, right? Would you confirm if you see the same picture that I'm seeing? Or do I need to draw it or do something else? Yes? Valeria, you closed your eyes, means if you want me to draw it? Draw it, okay. Guys, don't be shy. Talk to me, right? Simply talk to me, right? So let's imagine that we played. I cannot do 1 million; it's too complicated. But imagine we played 5 games, right? So this is game number. So this is game number 1, and in game number 1, you won $2 squared, but of course you lost. Well, I'll call it 10 to the 6 so that I don't have to write all the zeros, yes? And you lost 10 to the $6, yes? And then in game number 2, you earned, let's say, 2 to the power of $4, minus 10 to the 6 is what you lost. In game 3, you earned 2 to the $1 minus $1 million to the 6th power. In game 4, you earned 2 to the power of $3 minus $1 million. And maybe in game number 5, you earned 2 to the power of $7. You were very lucky, minus $1 million, right? What is the average number that you won, right? So because I always subtract minus $1 million, you can see that the average is simply 2 squared plus 2 to the 4 plus 2 to the 1 plus 2 to the 3 plus 2 to the 7. You agree? That's divided by 5 in this case, because you played 5 games. Are you with me? Divided by 5, and because I subtracted $1 million from each one of them, good, I was subtracting 1,000,000 from each one of them, so I can just say it's minus 10 to the 6. So on average, you see, because it's 10 to the 6 times 5 divided by 5. Yes? And what is expected value? Expected value is this. You see, if I do the average with 5 again, I will get entirely different scores. You agree? But if I have a very long table, then those scores will be regular. You understand? In other words, the average will start becoming regular. That's what I imagine expected value to be. Is that if I if I averaged only through 5 entries, that might not be regular. But if I average maybe through billions of entries, perhaps it will start being regular. Or maybe I have to average even more. I mean, see, the number of how many terms I average, it's not specified here. We need to investigate further the particular problem. The idea is that as I increase the number of entries in my column, as I play more and more games, as I make it more of an entrenched habit, the average will converge to a particular value, which I expect is, that's why it's called, which I expect is the expected value. Good? That's why you say expected value. It's just that average that you anticipate if there are many, many games played. Okay? Everybody understands the expected value? It's a very important concept. From this point on, it's a central concept in this class. Good? All right, so let's go back to this problem. Okay, so let's calculate the expected value. What would be the average? If I make a habit of playing this game, what would be the expected value? Yes? So let's consider what is my x. X is going to be the winnings, the amount of money I win per game. It could be 2 to the 1 minus 10 to the 6, or 2 to the 2 minus 10 to the 6, or in general 2 to the n minus 10 to the 6. You agree? If the coin lands heads on the nth trial for the first time, it's 2 to the n minus 10 to the 6. You're with me? And what's the probability of getting that score, 2 to the n minus 10 to the 6? If it's a fair coin, it's 1/2 to the power of n. Yes? So what's the expected value? I just add up the probability multiplied by the score. That was the formula we derived. Remember, guys? The probability times the score was what we ended up understanding, that the average in this huge table would be the probability of one particular score on the table multiplied by the score on the table, and you add up. I hope you understand it, guys, right? If not, stay after class. Don't leave without having a solid understanding of this concept. Now, let's multiply the 1/2 to the n through, guys. Multiplying it through, what do I see here? I see 2 to the n times 1/2 to the n. They cancel each other to 1. You with me? So it's summation of 1. I can take this limit to be n to infinity and just do the partial sum of 1 minus the summation of 10 to the 6 over 10 to the n. Which will be what? Which will be equal to the limit of n minus 1 minus 10 to the 6 times 1 to the 1/2 to the n. So it's really n minus 10 to the 6, where n goes to infinity. So your average winning for this game, are you hearing me, guys? The average winning for this game will be infinity. Infinity dollars. Do you want to change your mind? Are you playing this game now? Your average. You understand what it means? In other words, what does it mean? If you play huge many games, you will be getting huge rewards. If you played billions upon billions upon billions of games, you imagine that the reward might not immediately be infinite because it's just a finite number of columns, but it will be huge. Would you want to play this game? So Kazi says, let's play. Murshika says she still will pass. Why? Guys, so do you see it, or is it just that feeling that I got when I was looking at Magritte's painting? I mean, something is eerie about it, but I do not know what. Je ne sais quoi. Why are you passing if you're passing, or will you change your mind and play? Yeah, so who has a gambling problem here? What about, how many of you have read The Gambler? Have you read The Gambler already? I see in your eyes, no, not a lot of you have.
I mean, this is n goes towards infinity, but realistically, you're not going to play infinitely many games. And
yes,
how many?
True. But,
How many?
but if you don't play infinitely many games, I mean, you play lots of games and the number will be large. What does it mean n goes to infinity? It means as the number. What is this capital N? This capital N means possibly the number of games. As the number of games you play goes to infinity, the amount of money you will gain will be more and more and more on average, right?
So when does the conversion start?
Oh, that's a good question. That's a
Because
very good question.
if the conversion starts at like 1 billion, you're never gonna get there.
Well, you see, well, you hit it on the nail. That's that what you say, Americans, right? You hit you hit it on the nail. That's what you say. Yes, I've been to another state yesterday. At first I think, my God, wow, I've never seen Americans really, right? Well, now I realize that in New York, no Americans ever exist. I've been to Connecticut. In a place where they look at me like, what are you doing here? You Russians come.
When I went to Texas, they told me I look exotic.
That's great. Well, you do.
like a monkey or something. And they were like,
Well, I mean, I don't mind. I like when people look at me like a giraffe. If I could, I would be dressed as a communist with a star. Because as you know, guys, November
oh, actually,
7th,
you will match now. AOC will love you.
yeah, I know. On November 7th,
We'll put you on the right list.
Exactly. That's good, Valeria. You understand, right? November 7th was coincidentally the day of the socialist revolution. So you understand. So it's time to come there. They will welcome you with open arms. So let's go back to this topic, guys. Are you with me?
So it's not worth playing because it's too many games. You'll die before you get any more.
Exactly, Valeria. That's exactly what Shotaro said. Now let's look what is too many games. You understand? Maybe you could simulate playing million or billion games per second. Will you play it then, Shotaro? If I could simulate playing this at a billion games a second, so you don't have to throw an actual coin, it will be long, but 1 billion games per second, would you now play?
So 1 billion games per second.
Per second, right? So so you go to the casino and it will simulate playing 1 billion games per second. Would you play? Would other people that are quiet here, would you play?
It still depends on when the convergence is, because infinity is always going to be so far beyond 1 billion.
Possibly, yes.
So,
Wait,
I mean,
even 1 billion a second?
Sorry?
Even 1 billion a second?
That's the question, right? It's a difficult question here. So let me tell you how I thought of this problem further. So let's consider this modified St. Petersburg paradox, right? So some people, not in this class, because in this class most of you are quiet, they said, well, they would not play this game because if I get infinity dollars, that will be huge inflation, right? And inflation makes money worthless, right? If you read Remark, you would read quite a lot about it.
Yes.
Yes.
Yeah, you'll put them on fire.
Yes, you actually can use money for heating needs. Just burn them. So here is guys the modified St. Petersburg paradox. So instead of infinity, let's suppose that the game caps at capital N. Yes, caps at capital N, where N is, we'll figure out what this N is later on, right? So in other words, what would happen is that if you, let's say N is equal to 7, right? So you toss the coin 7 times. And if you never had heads, the game stops and you get 2 to the $8. You understand? 2 to the N plus $1 if you allow the coin to roll up to N. So that's the most you can get. Other than that, you get the same previous amount, right? If the coin rolls heads on the first or second or third or even 7th trial, then you get 2 to the 7th. You understand? But if it did not, if you never saw heads in the first 7 trials, then it's 2 to the 8. So in general, that would be capital N is the cap where you stop. Maybe not at 7, you stop maybe at another number N. What would be your winnings now as a function of capital N? Yes? So again, what happens here is now we have X is now only taking finitely many values, 2 to the N minus 10 to the 6, but the probability of X equal to 2 to the N minus 10 to the 6 is 1/2 to the N if N is less than capital N. And the probability of getting 2 to the N plus 1 minus 10 to the 6 is 1/2 to the capital N. Okay? I just calculated the summation, 1 minus the probability of not getting it before. So it's really 1/2 to the power of capital N. Are you with me? So let's look at the expected value now. The expected value is the previous sum, which reduces to n plus 2 minus 10 to the 6. Well, basically, that's what it reduces to. The summation, I hope you can do the arithmetic. It's n plus 2 minus 10 to the 6. And I want to know when is it bigger than 1? When, how large should this n? N represents how many tosses must I account for this to be so. Yes? So that means that the number, for this to be bigger than 1, bigger than or equal to 1, I need n it to be bigger than or equal to 10 to the 6. Do you understand? I need for this to be a worthwhile game, I have to have the possibility of the coin landing on heads on the millionth time. You understand? On the millionth time. So in other words, a fair coin, you flip it around, and only on the millionth toss do you actually see heads, and not before. That's really what this is saying. You know, million minus 1, essentially millionth time. Do you get me? For this game to be on average profitable. Yes? Now, what does it mean? The probability of this happening is 1/2 to the 10 to the power of 6. Yes? Now, let's see. So it's estimated that the number of atoms in the entire universe is about 10 to the 82 in the entire universe. Right? And 2 to the 10 to the 6 minus 1 is huge. It's bigger than 10 to the 200,000. You understand? Look at it, 82 to 100,000. Do you understand that you could build universes? You would, if you take each universe and make it into a particle, into one atom, you could build many universes. Right? You understand? It's enormously huge. So basically, the game is profitable, but you will not have the lifetime of the universe to observe how wonderfully profitable this game is. Right? It's kind of like my life. I will be successful eventually, right? When I'm dead. Good? Everybody understands what I mean? So I think it's basically this number of universes. Look at it, 10 to the 200,000 minus 82 universes. That's basically how many universes I can build out of universes. Right? It's basically something I cannot comprehend. It's a number so large that I completely don't comprehend it. So 1 billion games a second. You can even add a bunch of zeros. Don't worry, right? You will never see this game useful. That's according to this analysis. Make sense? How I figured it out? Because when you analyze the expected value, you realize that it's necessary to see outcomes that are very unlikely, like a coin coming up heads on the millionth time for the first time, right? And to see that, you will not see that in the entire history of the universe, in many histories of the universe. So you will just not see it. All right, so where are we now? Continuing with properties of expectation. Guys, let's quickly remember this very important formula. Y expected value of sum is sum of expected values. What is that expected? What is that change here of a random variable from one space to another? So I talked to Shotaro after class, and I think I mentioned one thing that might be useful for you in grasping this concept. Guys, what is a random variable? A random variable is nothing more than a relabeling of space, right? I can represent it even with the same space, right? So I can think of a random variable as S, and in S you have outcomes like S1, S2, S3, S4, S5. And I can imagine that what a random variable is doing is basically just a function that carries a bunch of those outcomes into just a bunch of those pebbles and melts them together. So maybe what happens is that S1 through S3 are melted into something I call, what should I call it? I should call it V1. right? It melts into V1, and then maybe the other two are melted into V2. Yes, and the function that is doing it, it's called x, right? So what happens is that the probability, so this pebble had probability PS1. This pebble had probability PS2. This had PS3. And now what's the probability of this guy? It's the summation, because they were melted together. It's the summation of PS1 plus PS2 plus PS3, yes? They were melted together. Now, another way to think about the same thing, look at it, the same picture, is to only imagine the same original sample space, yes? The same original sample space, but now the events S1, S2, S3 are relabeled, right? Each of them is relabeled as this is event V1, this is event V1, this is event V1. You understand? I relabeled them. And then the others S4 and S5 are relabeled as V2. You understand? So you can think of this as a relabeling as well. And so when I consider expected value, I am doing what? I can either look at V1 once and multiply by probability of V1, right? So I mean, I can calculate the expected value in two ways. One way is the expected value of the variable x. I can say it's just, let's say, V1 times the probability of V1 plus V2 times probability of V2. That's how it's defined, yes? But of course, looking at the situation, I can imagine calculating it entirely differently. I can imagine calculating it as, let's say, V1 times probability S1 plus V1 times probability S2 plus V1 times probability S3 plus V2 times probability of S4 plus V2 times probability of S5. Are you getting me, guys? So I see only a few people talking to me. What about the rest of you guys? If you are understanding, please confirm. Understand what I just said? And you, Alejandro, where did you go? Good. So that second presentation is very useful when I want to examine properties of expectation. So we proved that the expected value of that second property is the expected value of x is just going through S. And what is this x of S? It's just the relabeling, right? It's where x relabeled the different s's. So here S1, S2, and S3 were relabeled as S star. So that's just relabeling and multiplying by the original probabilities of the sample space. Good? So that is the second line that I wrote here. Everybody understands it? And that's what I did in proving that the expected value of x plus y is the sum of the expected values. Because I said x plus y is just the relabeling that x does to a particular event S plus the relabeling that y does to a particular event S times the probability that event S occurred. Understand this formula? And then I can distribute this probability and separate and see that I have the sum of expected values. And there was no assumption of independence or dependence of those events. We then solved a bunch of exercises. I hope you remember them. I don't have time to repeat all of them. Okay. And I showed you in this example that it can be complicated to calculate expected values when you are not using that idea. It's possible sometimes, but complicated. And at times it's very, very complicated. Okay. And then we calculated for matching problems. We observed that no matter how, if you have no matter how many people, if you have 5 people throwing and writing their name on a card, and then randomly each of them selecting a card, the probability that they will select their own name is always, well, sorry, the expected value of people selecting their own name is 1. No matter how many people play this game, on average, it's always going to be 1. That's what we calculated last time. Make sense? So we did a few other examples like that. Okay, guys, so here is the next example. Urn initially contains 1 red and 1 blue ball. A ball is randomly extracted and then replaced by 2 balls of the same color. Do you understand? So I extract a ball and replace it by 2 of the same color. So there's 1 red and 1 blue. Let X be the first time blue ball removed. Calculate the probability that X equals to K, where X is 1, 2, 3. Could be, yeah, so first time it's removed, right? So you play this game and then you remove the ball for the first time. You understand what I'm saying, guys? It will be removed. If I continue removing, if I just, what I do, I take a sample, I observe. If it's a blue ball, I'm done. If not, I try the next time. If it's blue, I'm done. If not, I continue. And every time I remove something and I did not observe a blue ball, I double that something. In other words, that means I remove the red balls and I double to each trial. Understood? Calculate probability that X is K, and then try to calculate the expected value, please. Kazi, 1 over X plus 1, what do you mean? What is X? X is equal to K? The question is, what's the probability it takes K trials? Okay, we'll see. Okay. Come on, guys. Faster, because I need to move on. And think about the expected value if you're done with the previous part. Okay, Erika, thank you. Naomi, what do you mean one? One is what? One is the expected value?
No, the probability.
But if the probability is one, then it's certain.
Well, because isn't, I guess my thought process, are you saying that blue is eventually drawn?
Well, I mean, you continue drawing until you draw the blue, and what's the probability it's on the cave trial? Maybe the probability it's eventually drawn is one, but what's the probability it's drawn on the cave trial? On the first, second,
Okay.
third. Make sense?
Mm-hmm.
Yes. Okay, so let's begin, guys. Yes, we need at least to do the probability, and then we'll figure the rest. Okay, so we can do it by conditional probability. Why not? Yes, conditional probability. So if it's on the cave trial, then you had red for the first k-1 trials and blue on the cave trial. You agree with me? So probability of red on first trial is 1/2. On second is going to be 2/3 because now you added another red ball, right? So there are 2 of them are red, 3 are in general. If again red, it's 3/4, blah, blah, all the way until k-1 over k. Yes? k-1 red, k together times, after this observation, I have k+1 balls. Yes? So it's what? What is it all together? It is k-1 factorial divided by k+1 factorial, which is, if I simplify, 1 over k times k+1. Agreed? Now, here I just quickly verify that the probability that blue will eventually be selected, guys, are you there? The probability eventually selected, like Naomi said, is 1. Here is the calculation. The probability it's eventually selected is summation from 1 to infinity of 1 over k times k plus 1, right? I sum out all finite events. And this is a telescoping series. Remember, Shotaro? You can actually do it another way, but it's a telescoping series. So it's 1 over k minus 1 over k plus 1. Summation of it, everything cancels except 1 in the last term. And the limit is 1. So I hope you remember such stuff. You can do it, I think, another way. Okay. So now let's calculate it. What do you think is the expected value? Can you do it quickly, guys? Because I really want to move on. And I don't want to spoil your fun. I really like when you figure it out. Expected value now. Okay. We know that the probability is 1 over k times k plus 1 that the blue ball comes on the cave trial. Okay, Naomi, thank you. Is it like an American way to say it? Or like, it's like infinity and stuff? I'm not good at imitating the accent, but you know what I mean, right? Like, oh my gosh, you know. You know what I'm talking about, guys? You can imitate it better. You know, like yes. All right, guys, let's work through it. Okay. Yes, Naomi, I'm not sure why there is a question mark. Should be right. Infinity. Now you see why. We just multiply it by k, and yes, Shotaro, it's the divergent harmonic series. Now, would anybody please tell me what is the interpretation? The expected value is infinity? What does it mean? I mean, I'm expecting to see the blue ball on the infinite trial.
Is it like the last or the Petersburg problem where like eventually you'll get to that average, but it'll just take a really long time?
But it's not a payoff. You see, in this case, we're observing, we're looking how, on average, how long does the game continue? You see, what is this in infinity is, I track, let's say the game is over when I pick a blue ball. How long does the game continue on average? Infinite long.
Is it because the longer you play the game, the less likely it is you pick a blue ball?
Exactly. So what is this infinity, guys? Let me summarize it a bit more precisely. If you were to play many games like this, right, you will see that as you increase the number of games you play, you will see that they are getting longer and longer on average. You see, you played one game, you played 2 games, 3, but if you played many games, you see that the average of the duration of the game is long. You play more games, you see it's getting longer on average. You understand? The games get long. So because you would have situations where you have more and more red balls, and you're not pulling anything out. Here is another one. Are you ready, guys? A fair coin is tossed. This one is hard, and this one is really hard. I don't know if I should leave you to think about it for a while. So a fair coin is tossed 16 times. What is the average number of times the pattern head, tail, tail, H will be observed? So you understand? You imagine that you write a word randomly by tossing a coin. So if the coin comes heads on first trial, you write H, then you toss the next trial and you write whatever letter comes out, and you have a word made out of 16 letters, yes? And you do this game repeatedly. So you generate randomly 16 letter words out of H and T. How many times within the word will you observe H, T, T, H? Right? So let me be clear here. So for example, maybe you observed something like this: H, T, T, H, T, T, H. How many times have you observed H, T, T, H? In this case, you have observed it one time here, and one time here. Yes? So altogether you observed it 2 times. Understood? So if I have a word that is made of H and T and is 16 letters long, randomly generated, how many times on average will I generate H, T, T, H? Nice that you made it, Melissa. Really glad to see you here. No worries. Don't be ever sorry that you come late. I'm glad that you come pretty much anytime. Okay, thank you, Alejandro. This is a bit of a hard question, guys. I do not know if it's fair for me to ask you to solve it in class live. Would you prefer that you think about it later and solve it then, or you would like me to reveal the answer? Let me know in the comments. Okay, so let's do it on Wednesday. Okay, guys, I'm skipping the solution to this problem. You think about it until Wednesday, and make sure to remind me in case I myself forget. It's very important, so remind me to go over this problem if I don't remember it myself. Okay. Great. So let's move to the next lecture sequence. Properties of variance. What, did I skip something? Strange. Variance. Okay. 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 I don't know why it's maybe I mislabeled something. But yes, here it is, right? It's weird. So now let's consider expectation of a function of a random variable. Okay, so what does it mean? It's very simple, guys. Look at it. Imagine that I carry out a sequence of relabelings, right? So imagine that here we begin with a sample space, and then this is first relabeling, and then S star is my next space, and I make another relabeling. So I can consider this as a composition of functions, which I call in this case the situation is as follows, right? So the function is x squared. So x is doing this. You see, it's mapping those outcomes to -1, those to 0, those to 1. Right, and then I want to know properties of x squared. What is x squared? X squared is yet another rearrangement, right? Because -1 and 1 are collapsed to the same event 1. 0 is collapsed to the same event 0. Make sense, guys? So there is nothing special about this new situation. So let's look at the difference. Let's say what happens, how we can calculate expected value, right? You might already guess that that pretty much I can consider the values squared multiplied by original probabilities for x, or I can calculate the expected value in the set S prime. You understand? I can calculate expected value in S star, or I can calculate expected value of S prime in using this variable. Okay, so everything's clear, guys. So there is this random variable x that converts the events 1, 2, 3, 4, 5, the original sample space with equal likely probabilities, into the space S star, and that's x. And when I ask what is the expected value of x squared is this. Now I'm working with S star, and I convert it to those values squared. Yes, and so I can calculate the expected value of x squared as 0 times the probability of 0 and 1 times the probability of 1, or I can calculate it as 0 times the probability x is 0 plus plus 1 times the probability that x is -1 plus 1 times the probability x is 1. You understand what I mean? That's because we're just dealing here with relabeling. Isn't that what I try to explain over here? Good? Do I need to go deeper into the discussion of relabelings, guys, or it's understood? Please confirm if you understand everything so far. If you came late to class, and at the beginning I was explaining how to view this entire situation as a simple relabeling. Make sure to watch the video if you haven't understood everything. So I only see 2 people. The rest are confused. Come on, fast, guys. If you understood, then yes. If not, tell me to go over something. No, don't delay it. All right, so I'm going on, guys. Now, I want you to be aware that the expected value of x squared is very different from the expected value squared, right? The expected value squared is just the expected value of x is simply -1 times the probability of -1 plus 0 times probability of 0 plus 1 times the probability of 1 squared. And that will be this number. Whereas the expected value of x squared is simply 0 times the probability of 0, 1 times the probability of 1. Understand? Everything that you're doing here is simply relabeling, right? In essence, what happened when I deal with x squared, it's like I'm having the original sample space, but the events 1, 2, 3, and 5 are labeled as 1. And the event 4 is labeled as 0. Make sense? Just to be sure. Okay, let me watch carefully, guys, right? So what do I do? What is X? X relabeling, really, I drew a lot of sample spaces. You can think of it just the same as if you are working with the original space, right? So when I say X, I have -1 here. What is this value? What is the -1? Is that this is -1? This is -1, this is -1, yes? This is 0, it's relabeled as 0. This is relabeled as 1. Clear? So instead of drawing a star, I can imagine that pretty much the names of the universes were labeled, and different universes are labeled with the same symbol. So universe 1 is labeled with symbol -1, universe 2 is labeled with same symbol, and onwards. Good? Now, when I say x squared, it means that everything that is labeled as -1 will be converted to -1 squared. Everything labeled as 0 will be converted to 0 squared label. Everything labeled as 1 will be converted to 1 squared label. So that means that now the next label is that this is 1, this is 1, this is 1, and this is 1, and this is 0. That's the x squared label. Understood? So when you're speaking about random variables, you might imagine that all you're doing is just taking the same sample space and giving the universes new names, and some different universes receive the same value. Or you can imagine the drawings that I drew here, that I'm switching from one sample space to another. Both are useful things to imagine. Good? And you all understand why the expected value of x squared is obviously very different from expected value squared. Because what this means the expected value of my game where I have the x squared label. Whereas what this means, this means, what's the interpretation again? This just means that I averaged something and I squared what I averaged. You understand? So it's an entirely different thing that you are doing here. Good? And here is that theorem, right? So in general, if x is a discrete random variable that takes on one of the values xk with probability pk, then for any real valued function g for which there is uniform convergence. Why uniform convergence? Because when you take expected value, you are rearranging the sum. And if you have infinitely many terms to add, technically speaking, you might rearrange the sum and create a different summation if it's not uniformly convergent. You understand? But the expected value is simply the label that outcome xk received, the new label that outcome xk received, times the probability. So that's what I'm saying. This is a rearrangement of sum. So for example, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 will converge, I believe, to a ln of 2, if I'm not mistaken, right? Or actually not minus ln of 2, I think, right? So so it will converge to minus ln of 2. Ln of 2 is less than, am I right? No, it will be ln of 2, but anyhow, right? So it will be ln of 2. The summation will be ln 2. If I rearrange the terms, then I will get a different sum. We can talk about it if you like, but that's technicalities for a different subject. So here is the proof, guys. So do you understand? Do you need another example to understand what the proof is saying? So the expected value of gx is just by definition is the different values that gx can take multiplied by the probability. And then what happens is that I just carry out a rearrangement, and I see it's the same thing as just looking at the labels individually. Let me again, I'm not sure you are not sure if I explained it well enough. Let me just give you a quick example. Good. So imagine that we have this sample space. Yes. So if I have the sample space, then imagine that we have outcomes S1, S2, S3, and S4. Let's actually have it S5, right? You will allow me to give them the same probability. So each has probability 0.2, okay? Each of them. Each of them has the same weight, okay? Just for simplicity, it doesn't have to be true. Now, what I'm going to do is create the function x. So the function x will pretty much just label S1 as let's say 2, label S2 as 2, label S5 as 2, and label the others as -1. Good. That is the action of the random variable x. Okay. Now tell me what happens if I now am not interested in x, I'm interested in x cubed, or I'm interested in, let's say, let's make it yeah, let's keep it simple, right? Let's make it simply x cubed. Okay, x cubed. What really happens? I said x cubed here. So what will I see? I will see that this becomes 8. Yes? It's just that I changed the label of 2 to a label of 8. I changed the label of 2 to a label of 8. I changed the label of -1 I kept it as -1. I changed this and kept it as -1, and this is 8. Good. So what is the expected value of x cubed? The expected value of x cubed by definition is simply is simply 8 multiplied by 0.2 times 3. We have 3 copies of it, right? 3 times 0.2 or 0.6. Good. Minus 1 multiplied by 2 times 0.2. That's what the expected value of x cubed by definition. I group based on the values that x cubed can take. It can take only values -1 and 8. Yes? But I can also calculate it out of order, right? I can calculate it out of order, and that's what I mean by rearranging terms, because I can also say that this is the same as 8 multiplied by 0.2 plus 8 multiplied by 0.2 minus 1 times 0.2 minus 1 times 0.2 plus 8 times 0.2. You understand that I now have the 8s in different order. They're not all together. Okay, that's the same. If it's finite, it's the same sum and just rearrangement of order. So all that theorem that I'm trying to explain is saying is that you don't have to adhere to the order of that is imposed by g of x. You can keep the original order imposed by x. Do you understand? So when I say expected value of gx, it's the expected value of, let's say all the values it can take are y's, right? So it's y1, y2, yj. So it will be yj multiplied by the sum of probabilities of outcomes that lead to yj. In my example, all the things that lead to 8, right? 8 multiplied by the outcomes that lead to 8. But then I can move the y in, and that y moved in can be converted to gxk. Here it is. Yes. And then when I look at the summation, I just rearrange the terms, and I see that I could have kept the original ordering imposed by x. Do you understand what I mean? Here is again another illustration of it. So imagine that that we have x is taking numbers plus or minus 1, plus or minus 2, all the way to plus or minus x, plus or minus n, and the probability for n or minus n is always 1/2 to the absolute value of n plus 1. Okay, and then let's say that y is the absolute value of x. You understand? So when I say y is absolute value of x, it means I no longer have negative numbers. I only have 1, 2, 3, 4, etc., all the way to n. By definition, the expected value of y will be the summation from n1 to infinity of the, because you see it goes on, right, of n times all the numbers where absolute value produced n, right, the probability pk. So that would be n multiplied by 1/2 to the absolute value of n plus 1. That's when k equals to minus n, and 1/2 to the n plus 1 when k is equal to n, based on this formula. Good. And when I simplify it out, it's just summation of n times 1/2 to the n, and that summation is equal to 2, as you can easily verify, because this is, why is it 2? I can do it. Naomi already did it when we had the discussion. It's like with the pistol. It's like a 2-chambered Russian roulette, and this is asking how long is the game going to last. So I know right away 2 rounds. Or I can do the algebra as I illustrated before. Yes? So you understand, guys, I calculate the expected value by definition. In other words, I adhere to the ordering imposed by this y, right? So it's what's the probability of 1 multiplied by outcome 1, right? That's what we have here. But what produced 1? It could be a negative number that produced 1 or a positive number that produced 1. On the other hand, I could have instead done the summation for n from minus infinity to minus 1 of absolute value of n of 1/2 to the absolute value of n plus 1, plus the corresponding summation from 1 to infinity. You all understand that n, basically my random variable can take all integer values, maybe not zeros, but all integer values other than 0. That's the idea. And I gave you the probability, right? So here I adhere to the original value that x could take. And I see that calculating the expected value doesn't change anything this way. Good? Everybody understands what I mean? Do I need to give you another example or what? Or do you get it? And the rest of you guys? Yeah, so confirm. I mean, come on, write Y or something, or G or something, so I know you get it, because maybe I explained it and you don't understand it. Oh, great. Great. Thank you. Okay, here is a corollary. The expected value of a times x plus b is a times the expected value plus b. Yes? Why is that? Well, because I can simply use the original ordering of x and say that it's just ax plus b times the probability that x occurs. I keep the original ordering. And if I keep the original ordering, I can quickly distribute the sum and see that the result is true. Right? It's just it's a times the expected value of x plus b times the summation of all the values that x can take, the probabilities, right? Which necessarily have to add up to 1. So it's a times the expected value of x plus b. Good? So I should relay both, guys, but you see my lectures, I gave them wrong sequence, right? This should have been, so this should have been the next lecture, and it's labeled as something else. I'll look at it. Okay. I figure I will pause at this moment since you probably want to go, and yeah, do you have any questions, guys? No? Are you sure, right? So what I said about relabeling is entirely clear. It's clear as daylight for everyone. I see hesitation. All right, so let's draw another example, maybe. Suppose that that what you have is you have 6 events, right? S1, S2, S3, S4, S5, S6. Okay, and each just out of convenience, I will label each as 0.16 basically. Each of them is 1/6. Okay, each of them is 1/6. Now, first, the relabeling is that let's say those guys are going to be mapped to the number -1. This is going to be mapped to the number 2, and this are going to be mapped to the number of -2. That's what x is doing. Okay. Now I'm going to consider what is the absolute value of x. Okay. So I want to convert the labeling into absolute value of x. Okay. Absolute value of x makes -1 equal to 1, makes 2 equal to 2, and makes -2 equal to 2, right? So by definition, what is the expected value of absolute value of x? By definition, it's the numbers that we take. We can begin with the smallest number and then the next smallest number. So it's 1 times the probability of getting 1, which is 1/2, right? Or 3/6. You agree? It's 1 times 3/6 plus 2 multiplied by 3/6. Agreed? Because there are going to be two numbers that give me 2, and altogether it corresponds to S4 through S6. So it's 2 times 3/6. Good? Now, I could have carried the initial ordering that was given by x, -1, 2, and 2, right? So for example, I could have calculated the expected value of absolute value of x this way. I could have said it's equal to 1 multiplied by 3/6, yes? Plus 2 multiplied by 1/6 plus 2. I keep the labeling of absolute value of x, but I go like this. I go this first, then this, and then this, yes? Plus 2 multiplied by 2/6, and I would have gotten the same thing. You see the difference? Look at the difference. Before you go, guys, look at the difference here and here. Do you understand that what really happened was simply rearrangement? Yes, because what's the rearrangement? Look at it. 2 times 1/6 plus 2 times 2/6. I can factor out the 2, and I have 1/6 plus 2/6 is 3/6. Yes. So it's a rearrangement of a series. Now, if it's finite sum, there is nothing special about it. But if it's an infinite sum, then you run into trouble, right? Rearranging any infinite sum can cause a problem. But if you have an absolutely convergent series, then any rearrangement gives you the same result. Okay. And that's not a trivial thing, because we can use rearrangements to notice other features of the summation. Good. So with this, I leave you alone. I hope you're finishing up the exam if you haven't submitted it, and that you did a good job with it, and that you have not felt the need to do something inappropriate. Good. Take care.